Okay, it's our great pleasure to have Professor Chen from Peking University to give the last talk of this semester. His topic is operator algebra and algorithm for topological sleeve-level codes and gap boundaries. Let's welcome.
Yeah, okay, thank you for the invitation. It's my pleasure to be here. It's my second time to be here after the summer's event. And today I will focus on my recent two paper. Sorry.
这激光笔可能不太好用，你就指就行。
Okay, so based on the two paper there. So first I want to thank my collaborator. So Zhijian is my student, and Bo is the postdoc at Harvard, and all other two people are the students at University of Maryland. So today, although my topic is a little bit abstract, but it's a very engineering talk. So my motivation is I try to find a better torical or better surface code, which is good for experimental realization on the superconductor. The superconducting quantum computer. How do I flip?
Okay.
Okay, next. So first part is the motivation. So first I will introduce some background about the recent progress, and later I will review the famous topological order, the key-type torical, the color code, and some modification. So and then I will introduce our algorithm, try how we extract topological order using the polynomial combination. And finally, if I have time, I will want to go through some boundary construction, because on the real experimental platform, we only have the surface version of this quantum computer. So we don't actually have the toric structure. So I will comment on how do we make the toric code become the surface code. Okay, so first, the motivation is obvious. So we want to build some quantum computer, and we need to overcome many noise and some faulty operations. Yeah, so typically there are two strategies for doing this quantum error correction. The first one, the bottom one, is called Pauli stabilizer code. So actually, this is the first proposal back to the early 90s. I think it's around 1995. Peter Shaw, he already proposed the Shaw's code, which uses 9 physical qubits to encode 1 logical qubit, and we can correct any single qubit error. And similarly, the Sting, he proposed his 7 qubit code, and this 7 qubit code can be generalized to the color code. And generally, we have the CSS code proposed by 3 people named here. Yeah. And so this is the one strategy. And the other one is use the topological phase. So we call it topological quantum code. The most famous example is proposed by key-type around 2005. It's called toric code. So we use the Hamiltonian, so where is a degenerate response state, and we use this degenerate response state to encode some quantum information. And later on, we have generalized construction to quantum double. And similarly, the Xiaodong Wen and Michael Levin, they have their own string name model. And more generally, the digraph-Witten topological quantum field theory can also be understood as a generalized version of a quantum error correction code. So in today's talk, I want to combine these two approaches. So I want to study the topological quantum code such that it can be represented in a Pauli stabilizer formalism. Let me just briefly give a review. So what's the definition for these two methods? So as I mentioned before, for the topological quantum code, it's like we design a Hamiltonian, which is corresponding to some topological phase, such that it has a quantum state degeneracy. And the most important part of this quantum state is that those quantum states, they are locally indistinguishable. So which means if we have any local observer or local perturbation, we cannot go from one state to the other one. So this is a topologically protected quantum state. And next one, the Pauli stabilizer code. So this is actually more simpler. So we just write down some Hamiltonian, and the Hamiltonian is some over some stabilizer. The only requirement of the stabilizer is we require the stabilizer to commute with each other. So solving this Hamiltonian is actually trying to solve the simultaneous eigenstate of each stabilizer. So this Hamiltonian is actually easy to solve. We just need to focus on each SI. So SI is some product of Pauli. So we just have this the eigenstate of each SI, and the solution of this Hamiltonian is just a simultaneous eigenstate of each SI. And these two of course has their own pros and cons. So for topological, the obvious advantage is it's naturally protected from any local error. So this is the definition of topological order. So this one that they are not distinguishable by any local observable. And also the protection scale with the system size. If we try to increase the system size from 10 to 10 to 20 to 20, the protection actually increase. So this is actually already be observed in the experiment. So there's a paper by Google just this month, maybe December 10th. So they have a paper on Nature. They have realized the detect surface code on their superconducting qubit device. So they test the square. It's a very small system. They go from a 3 by 3, 5 by 5, and 7 by 7. So their experiment demonstrates that they already achieved a threshold. The threshold means when the error rate is lower than roughly 1%, you use a larger and larger system, the performance becomes better and better. Yeah. So it's the first time people realize that our experimental device has already achieved the threshold of the toric, and this has already been tested on the device.
Excuse me, I have a question. So from the series point of view, how to understand this protection scale, which is a protection spectrum when the scale is large?
So this depends on what's your logical operate. So in the torical case, it's like we have some polar structure. If we need to go from one state to the other state, we need to find a logical operate, so which is a string operate along the large cycle. For example, if your system size is 10 by 10, then I need to apply 10 Pauli operate at the same time to go from one state to the other. If my state is 20 by 20, I need to apply 20 operate at the same time. So once you increase the system size, the Pauli weight required to go from one state to the other actually increase. So which means it has a larger codistance. So it's less likely we have some random error which can cause one state to go from the other. Yeah. Okay, on the other hand, for the polynomial, the benefit is it can be executable. So it's easy for us to analyze. It's like error correcting property. So for example, given a syndrome, how do we use the decoder to find a location of error? And it's also easier for physics implementation. However, so on the usual polynomial, it's usually not scalable. So if I just propose a Peter Shor's code, the 9-qubit code, it's not easy to see how do I extend this error correcting code. Yeah. So today I want to combine these two. So I hope our design have the advantage of both sides. So it has some natural protection and it's go with the system side, and also it's executable, and we can easily analyze the behavior of like decoding. Yeah, so rhetorical is the more simpler example for satisfying these two conditions, and I will try to propose some kind of modified torical or generalized torical.
Sorry, how do we know that like combining both won't have both disadvantages?
Yeah, that's a good question. So yeah, so this requires some careful design. So we need to make sure that, for example, the disadvantage of this topological coil sometimes is very complicated. So like the diagonal equation theory of the quantum number, although by some physical intuition, we expect it has some long distance, but actually it's very hard for you to analyze. Like given some syndrome, you cannot even diagnose where is the error. It's a very complicated structure. So if we have some exact solvable model, it's much easier to do. Yeah.
Then, like on the other side, the fact that you have limited protection or like non-scalable protection could that be bad enough such that the topology doesn't matter anymore? Like the
Yeah, that's a very good question. So recently there is some proposal they construct a complicated LDPC code. They have a good scaling. So which means the logical rate is a constant and the distance scale with the physical qubit. And so it's a design more from a graph theory. So it's something called expander graph, like a Ramanujan graph or something. And now people already try to use the idea of topological order to understand this code. So although they have some complicated design, but I think there's a general belief, okay, so you can understand everything in terms of topological order. Yeah.
Okay. Thank you.
Okay, so for the next session, I will quickly review the famous one, the toric and their generalization. Yeah. So since I believe the audience, you are expert, so I may not explain every detail, but let me just quickly remind you what's going on for the toric. So the toric is many names. So sometimes in quantum information, people call it P-type surface code. And I'm more used to call it a toric code. It's already it's the original proposed on a torus by P-type. And in the hydrogen theory, they call it a Z2 gate theory. But actually, all of this name they refer to the same model. So yeah, so I will just try to explain here. So now consider a square lattice, and on each edges, I put the qubit or Z2 spin here. So therefore, I have the Pauli matrix which can act on every edges. And here we have the vertex 10 and the plaquette 10. So for the vertex 10 is around the vertex, I apply the Pauli matrix X around the edges. And here for the plaquette 10, I apply the Pauli matrix Z along the edges of a plaquette. A very important property is these two terms, they commune with each other. Because every time you move the plaquette close to a vertex, their intersection is either 0 edges or 2 edges. So when we have 2 edges of Pauli X and Z, when we exchange the order, it gives a -1 to the power of 2. So it doesn't give any sign. So these two terms they commute. So this is the commuting stabilizer Hamiltonian. So the ground state satisfies each vertex and its plaquette equal to +1. So this is the simultaneous ground state. So if we put it on a torus, there will be actually 4-4 degeneracy. But so far, let's just put on the infinite plan. So let's just don't worry about ground state degeneracy at that time. Then we want to analyze the excitation of this particular Hamiltonian. So there's two types of excitation. First, I can apply some Z, Pauli Z string operator along this blue line. And you can notice this Z string will anti-commute with certain vertex term. So first, let's focus on the plaquette. Your plaquette is always Pauli Z, and Z and Z they always commute. So this Z string doesn't violate the plaquette. But however, if we pull a vertex term near the endpoint of this Z string, and we can say this Z string is violate single vertex term. So we can see this Z string create excitation around its endpoint, and we call this endpoint the E charge, the electric charge excitation. And similarly, we can apply the Pauli X operator on these red vertical edges. And notice this Pauli X always commune with this Pauli X, so this only violates some plaquette. And this plaquette, if we put it at the endpoint, it has a anti-commutation with this Pauli X string. Yeah, so this X string will violate two plaquettes here and there. So we call this plaquette violation. It's called M particle, the magnetic flux excitation. Yeah. So this is basically the Z2 version of the standard electromagnetism. So E stands for charge and stands for flux. And there's a very important property. So it's called a horizontal Spohn effect. When we move the charge around a flux, we will pick up the U1 phase. In this case, because this is the Z2 gate theory, the U1 phase we only can get is a -1. Yeah. So this is called the anyon theory, correspond to this toric Hamiltonian. So we analyze the low energy excitation and we call this particle an anyon. So E and N will generate the whole anyon theory of the toric. And similarly, this toric can be generalized into higher dimension. So here high dimension means I extend the qubit into QD. So here, notice usually the qubit stands for the BIT stands for like there's a 0, 1, 2 state here. And actually we can consider like the 4 stages in here, 0, 1, 2, 3. And in this case, we can generalize the Pauli matrix from 2 by 2 into some 4 by 4. And of course, the algebra will change a little bit. So originally, when we exchange the Pauli x and z, we get a minus sign. And here, we get a factor of I here. So for the Z4 gauge theory, we can write down a similar Hamiltonian here. But here, we need to be a little careful about the dagger here. Because here, there's a factor I. So I and minus I, they are different. So we need to make sure we put the dagger into the right place, such that the pluggator and the vertex then they commute. Yeah. So in this particular example, the Z4 toric, we can see there's actually a 16 for bounded degeneracy. Yeah. So here the bounded degeneracy on the torus is proportional to the number of anyon. So in the Z2 toric, the E anyon and A anyon, they are order 2. So we have 2 times 2 equal to 4 different bounded degeneracy. And here, the E anyon and A anyon, they have order 4. So 4 times 4 equal to 16. So you have a 16 for bounded degeneracy in this Hamiltonian.
And this is the semyon, right?
Semyon or? That's a good point. So Z4 toric is different from double semyon. So I will mention a double semyon later. Yeah.
Okay.
But so actually, the double semyon can be embedded into the Z4 toric. Yeah.
Okay. Right.
Okay, so now let me step back from the latest model and just focus on how do we classify the anyon theory. So from now on, we can just forget about microscopic detail and try to focus on what is anyon behavior. Because of the latest model, we can actually write down infinite number of them. Yeah, for example, I show you the Z2 toric, Zn toric, and there are so many other constructions like color code and the recent construction, the BB codes, and the one plus K model. So actually, you have an infinite way to write down the stabilizer code you like, as long as each time they commute. But actually, some of them, they are actually equivalent. By equivalent, I mean they have the same anyon behavior. For example, there's a paper by Benjamin Yoshida. He has already shown that if we have some color code, we can apply some quantum circuit to transform the Hamiltonian. Because we can always conjugate the Hamiltonian without changing the spectrum. So we can apply some unitary to conjugate the Hamiltonian to make the color code look like exactly 2 copies of the Z2 toric. Yeah. So this is called a folding. So in his paper, he showed that if we have 2 toric and I can fold one to the other, and this can become a color code. So this is just some example. So although in the Hamiltonian level, we can write down something look very different, but their underlying physics, they're actually the same. Okay, so what's the anyon theory? And because there are so many experts here, so I don't want to go into the mathematical detail, but let's just focus on a very simple example of abelian anyon theory. The abelian means the fusion rule is a group-like structure. So when we have some group element A times another element B, it will become the third element. Yeah. And the only data required for the abelian anyon theory is their own Chen statistics. So let's tell us the particle there is boson, is fermion, is semyon, or anything which is a U1 phase here. So we need to specify the anyon label, like the E and M anyon, and their fusion rule, and their topological spin data. And with this, let me tell you a theory. So this theory is proved by Bin and later by Zhou Wenhua for more general setting. The theory is following. So given the stabilizer Hamiltonian using the ZPQD. So ZP, the P is prime. So for example, if we use the Z2 cubic, the 2 is a prime number. So this theory applies. So you can write down any Hamiltonian as long as it's translation invariant. We can always find some quantum circuit U to diagonalize it, not diagonalize, to conjugate its H such that it becomes finite copy of toric. Yeah. So this theory is very strong. So which means given some Z2 qubit system, no matter how you design your Hamiltonian in any complicated way, as long as it's a 2D Hamiltonian, has some translational invariance, you can always find some canonical basis to make them look like finite copy of the Z2 torical. Yeah. So this is some underlying message. No matter how you design your Hamiltonian, it's always like torical, but just in some maybe different way. Yeah. And this theory only works for the Z P when P is prime. So there's a natural question. Okay, if P is non-prime, can we find a counter example? Yeah, the answer is yes. So let me show you an example when the qubit is a Z4, the Z4 qubit, and I can show that in this particular Hamiltonian, the underlying theory is the double semion. Yeah. So this derivation is in my another paper with my collaborator Tyler and Nate. So we first start with the Z4 torical. So the Hamiltonian actually looks like the Z4 torical. For example, this is the Z4 torical vertex 10, and this is the placket. But we need to do some modification. So once we do this modification, it's called anyon condensation. So once we condense the E squared and N squared anyon in the Z4 torical, this becomes a double semion. So the double semion is very similar to the torical. So it has 4 different anyon, and it has a bosonic charge, but the flux is changed. So in the original torical, the flux N is also a boson. And now this flux becomes a semion. By semion means when we try to exchange two particles, the phase vector is the plus is the I instead of the -1. When it's -1, it's called a fermion. When it's I, it's called a semion. It's like a semi-final. We cut the fermion into half. It's called a semion. So this name is, I think, it's invented by Professor Xiaogang Wen. So this is just a particular example. We can find, so in the Z4 qubit, we can find some complicated design Hamiltonian such that the underlying theory is beyond the torical. Okay, now let's go back to the Z2 case. Although I said that the Z2 case is kind of boring because no matter how you design the Hamiltonian, it's always finite copy of a torical. But so this is more from a theoretical point of view. But from an experimental point of view, although all of them are torical, but some of them they perform better, some of them actually perform worse. By better and worse, I mean just some experimental parameters. For example, for each stabilizer, how many Pauli I need to apply. Sometimes, like a torical, sorry, let's go on torical here. The torical is the weight 4 Pauli, so it has only 4 Pauli matrices. And for the color, it has a weight 6 Pauli matrix. Yeah, so 4 is less than 6. So we will say that sometimes torical is better than color from this perspective. Yeah, more standard is like for every core, we have the NKD parameter. We use the N physical qubit to encode K logical qubit, such that codistance is D. So we always want to find a better NKD. For example, you increase K is nice, you increase D is nice, you decrease N is nice. Yeah. So here I show you 2 different generalizations. So the left-hand side is like from the torical, the original stabilizer contains only 4 Pauli X here. And now I introduce 2 extra X. So here my stabilizer becomes this product of 6 Pauli X. And similarly, I need to change the plaquettes. The original plaquette has this 4 Pauli X. And now I need to tensor product with other 2 Pauli Z. So I increase the weight from 4 to 6. So each stabilizer becomes weight 6 Pauli. So this is not proposed by me. So this is proposed by IBM. So IBM in the last year, he has this year, he has a paper on the nature. They modify the torical and they claim the performance of this code is roughly 10 times better than the original torical. By 10 times means it's like when we fix the N and D, so we use the same number of qubits with the same protection D, and they increase the logical qubit by roughly 10 times. Yeah. So it's quite amazing. So it's like we just do some little modification and its experimental performance becomes much better.
Right, but that's still topological.
Yes, so we will show that this model is equivalent to 8 times of a toric.
Okay.
Yeah, because my previous theorem tell you, okay, I can find some circle U, finite circle U to conjugate this Hamiltonian become some finite copy of the standard toric. Yeah, so although this Hamiltonian look very weird, but according to the theorem, they must exist some finite circle. If we conjugate this Hamiltonian, this become exactly a different copy of the toric.
Oh,
Yeah, although it's highly non-obvious,
yeah.
it's not doable by human ability. Yeah.
Okay.
Yeah. So it's still quite magic. Although we already know this must be some finite copy of toric, but actually it's yes, a lot of freedom we can play around to improve its behavior. Yeah. Now, similarly, it has some other. So this is done by me. So given from color code, it's some product of poly X around this 6 vertex, and also the product of poly Z around this six vertex. So in this case, we put a poly on each vertex of this honeycomb like this. And similarly, we can try to modify its stabilizer from this to here. So we add some 2 extra dot here, and similarly we can add more. So as long as the dot you add is symmetric, this can always commute with itself. So each of 1, 2, 3, 4, 5, 6 correspond to a self-commuting Hamiltonian. Yeah. So we can also generalize the color code. So the naive question is, given this generalization, how do we systematically study its topological order? So for example, how many logical qubits it can encode, and what's the code distance? Yeah, so this is my motivation. I want to develop some efficient algorithm, like given any input stabilizer, I can tell you what's the topological order, like what's the anyon, and some corresponding code parameter like NKD. Let me get some water. Okay. So this is some demonstration of our algorithm. So first, given a stabilized model, for example, like the poly X vertex 10 and poly Z plaquette 10. So given a Hamiltonian model, first we analyze how each single poly will violate stabilizer. For example, if I apply some poly X here, it will violate some local stabilizer around this poly X. So this we call it a syndrome. Syndromes mean we will violate the stabilizer. So given this syndrome of the single poly, we use some computer. So we try to assemble this poly to form some string operator. And we want to make sure that this string operator only violates some syndrome at the endpoint. Yeah. So this can be done by computer. Yeah. So once we find the all string operator, we can find the all possible anyon. And we can use the anyon braiding and fusion to detect their property. Yeah. So from this, we can determine the abelian anyon theory from a given poly stabilizer code. Let me just show you some results correspond to previous generalization. So here, each number like 1, 2, 3 correspond to one type of stabilizer model. So in the original honeycomb color code, so it's example 1 there. We can show there is a 2 copy of a Z2 toric code. And similarly for other things, like for example, example 6 here. So it's like we have the plaquette 10 with 2 extra dots here. So this is my stabilizer. And this model corresponds to 6 copy of a Z2 toric code. Yeah. And similarly, we have some other example, even in the Z4 qubit, and we can detect some double semyon topological order or the 6 semyon topological order. Yeah. So this is just some numerical result. We can apply our algorithm to analyze this kind of example. And similarly, so this is the BB code, the bivariate bicycle code I mentioned before. So this code is proportional by IBM. So they have modified the toric code with these 2 extra legs. So this two extra legs, the position can actually be moved. If I can, for example, this A can be any number. So this corresponds to A equal to 2. If I have A equal to 3, this will move this X to the up. Yeah. And similarly, if we move this one, we also move this one correspondingly. So once, so this design, make sure this X and Z, they always commute. So we have some parameter, we can adjust the stabilizer. So this is the table I find. So let me explain in the details. So first, the vertical direction corresponds to a different value of A from -3 to 3. And the horizontal value corresponds to B, the B from -3 to 3. So in their paper, so I will show you the next slide. So this is the picture from their original paper, correspond to this A equal to B equal to 3. Yeah. And the K here means the number of anyon in this series. It has 16 anyon. 16 generated. So by generator, I mean in a toric, we have E anyon and N anyon. So it has 2 generators. And now we have a 16 generated. So which means in this series, it corresponds to 8 copies of the D2 toric. And but here I have another parameter L. L is very important. Because in the original toric, anyon can be moved by any distance. So I have an E anyon here. I can move by one distance, go to the right and go to the top. And by L equals to 12 here, I mean the anyon can only be moved by the distance of 12. Yeah. So although it's still mobile, it can still be moved around in your lattice, but the distance it moved must be the multiple of 12. So this will put some constraint on your system size. If we try to observe all possible 16 anyon, we need to make sure the system size is the multiple of 12. For example, 12 by 12 lattice. Yeah. And so you can see there are some other examples like the 2 minus 3. So you can see the anyon number is 20. It's very nice. So it's 10 times better than the toric. However, the distance is 341. So which means if you want to observe all possible 20 anyon, you need to make sure your system size is actually length of 300. So this is very bad for experiment. But for experiment, the best thing we can do is maybe just 10 by 10, 20 by 20. So this has 100 of cubic. So for this very large length, like a 1000, it's very unphysical. Yeah.
I have a question on the last previous slide.
Sorry.
Yeah. So what I noticed here is that for the 6 different modified color codes that you have, 5 and 6 are non-local, like
in some but I will still call them local, although the range is a little bit large.
Yeah.
But if you just put it on the infinite lattice or very large lattice, each time is still just I call them a local stabilizer.
Yeah, but the point is that if I look at the unit cell, it's translationally invariant.
Yes.
If I look at the unit cell, then each term will have operators that kind of goes outside.
Right.
Yeah, and I see that I'm making that comment because the topological order is no longer toric codes. Right?
It's still toric. 600. Yeah, so ignore the last three row.
Okay. I think I'm mistaken. Okay. Yeah. So the last 3
it corresponds to some weird model. Yeah, I didn't have time to mention it. So this is in my paper. Yeah.
Okay.
So here I only have the 600 already.
Oh.
So as long as it's a Z2 cubic system, it must be some finite copy of the Z2 toric.
Okay, so locality kind of doesn't.
Locality can increase this number. So based on my observation, if you have some longer locality, possibly will encode more logical information.
Mm-hmm.
Yeah.
But there's also a theorem by like Kapustin and this one other person that like you can't describe the Chen insulator using
by Tchaikovsky and Kapustin. Actually, Kapustin was my advisor. IT student. So I think the conclusion is you cannot construct a chiral theory.
Mm-hmm.
Yeah. So Yeah, as long as you write down stabilizer, it must be some non-chiral. So actually, in my previous paper with my collaborator Nate and Tyler, we showed that we can use the Pauli stabilizer to construct all possible abelian quantum level. Yeah.
Okay.
Okay, so let's go back to this slide. Yeah, so let's show that we can vary the different parameters for this modified toric code or the BB code. So we can obtain some table. So this table will give us some guidelines to say, okay, in some case, this will perform better. So in particular, this example, let's put, so if we put it on the 12 by 12 lattice, we will have the logical qubit has a 16 different there. So in the original paper, they only put on the 12 by 6 torus. And the parameter they obtain is 144, 12, and 12. Yeah. The reason is because the k equal to 16 can only be observed at the length 12. If we have the length only 6, if we try to solve what kind of anyon can be moved by distance 6, there are only 12 of them. So that's the reason why in their code, they only have the 12 logical qubit. Yeah. So actually, if we put it on the 12 by 12 lattice, it will become 288, 16, and 12. Yeah, so like I write here. Yeah, so if we can scale this into infinite, like a arbitrary large torus, like we can multiply any L here. So you have the 288 L squared, and this k is always constant, and the distance is proportional to L. So we can compare this parameter with the standard toric. So they have the same scaling because for any 2D code, there's a bound called BP T bound, like a KD squared divided by N must be constant. So K times D squared divided by N. So in this case, is 8. So 16 times 12 squared divided by 28, yeah, it's 8. So in the original toric, the content is very bad. So the content 2 times 12 squared divided by 28 is 1. So I increased this number 1 to 8 from this modification. Yeah. So this in the paper why they claim this is roughly 10 times better than original toric. So the price we need to pay is for each stabilizer, it becomes a little bit non-local. So this is why they draw the figure. So each square corresponds to the stabilizer. So the check is correspond to the stabilizer. The figures mean the stabilizer contains the 4 nearby Pauli X, and 1 go from here to here, and 1 go from here to here. So for this X check, it has 6 Pauli X. So this is how we read the original figure, but this figure is just exactly the same as this figure. Okay. So any questions so far? So this is more like some experimental trial. We can try to modify the toric to see how they perform. Yeah. And now I will become more mathematical and give some foundation how we actually develop our algorithm. And now, let me define the anyon in more systematic way. So consider I have some lattice and even include a boundary. But let's just forget about boundary. Let's just focus on the bulk here. So according to our toric picture, we can apply some string operator such that it only violates some stabilizer at the endpoint. For example, I will violate this vertex 10 and this vertex 10. So I have this phi 1 and phi 2 equals to -1. So in general, you can consider the anyons as some local pattern of this evaluation. Yeah. So mathematically, it's the homomorphism from the stabilizer group to some U1 phase. So in the toric case, this U1 is only Z2. So I copy this from my paper. First, we prepare some ground state. Then by the definition of ground state, when we apply each stabilizer, it must have some +1 eigenvalue. However, if we apply some Pauli operator n, so this will modify the bound state. So such that my stabilizer apply on this modified bound state, this will give some excitation. The phi become to +1 or -1 in the torical case. Yeah. So any violation from stabilizer to some U1 value is called anyon. And there's a very important theory in 2D. Any anyon can be created by some string operator. So this is a very strong theory. It tells me if I have some local violation, so I tell you, so locally, okay, this placation is violate, this starting is violate, I can always create this violation by some string operator. So this will become an endpoint of string operator. So this is very special in 2D. So this, in the higher dimension, this theory doesn't hold. The counter example is the fractal. So there's a very hard research in the last maybe 5 years. They studied a fractal model. So it's proposed by Zhu Wenhao. So they have some 3D model. It's a Pauli stabilized model, and it also has some particle excitation. But this particle excitation, it cannot be moved. It can only be created by some fractal operator. So by fractal, I mean you need to apply some tetrahedron, and it will transform this one particle into 3 another particle on other lattice. Yeah. So in the 2D, every anyon is mobile by string operator, but in the 3D it's not. So there's a huge difference from 2D and 3D. So that's why the 3D stabilizer code is much more complicated than 2D stabilizer code. Yeah. And using this concept, we can define the so-called equivalent anyon. By equivalent means if I have some local violation here, and now I apply some local Pauli matrix around here, this will change the syndrome here. For example, it will change this syndrome into some other syndrome. And then we will see these two syndromes, they are identified. Yeah. So this is the mathematical definition, how we define anyon and their equivalence relation. The anyon is defined by the homomorphism from stabilizer to the U1 phase. And the equivalence is two syndromes, they are the same if we can obtain from one to the other by some local Pauli operator. Okay, so given the anyon and their string operator, we can define their topological spin. So this is on the lattice how we define their topological spin. So first, I prepare the initial anyon at 1 and 3. So they are actually the same anyon, but I use different color for you to keep track of them. So the first step, I move the red anyon from 1 to 0, and then 0 to 2. And now then I move the blue anyon from 3 to 0 and 0 to 1. And finally, I move the red anyon from 2 to 0 and 0 to 3. So you can see after this 6-step unitary operation, the position of 1 and 3, they exchange. And this process is designed such that all other ambiguity are cancelled out. For example, you can modify the U1 by any phase, and this U1 inverse will have the inverse phase to cancel out. So no matter how you choose U1 or how you position your particle here or slightly different, this process will guarantee you get some topological invariant, and this topological invariant will give you the exchange statistic of this particle at 1 and 3. So this is proposed by Michael Levin and Xiaodong Wen. So it's usually called a T-junction process. So given this, and previous slide we obtained the anyon and string operator, we can obtain the full data of the anyon theory.
What's 0?
0 is just some vertex. So like a 0, 1, 2, 3 is just the label of 4 vertex.
Yeah, but this is on the lattice, right?
Yeah.
So if I have a trigonal lattice where I 1, 2, 3.
I assume my lattice contains this 4 point. Yeah.
Okay.
Yeah.
But
And
for any lattice, I'm able to kind of perform this T-junction.
yeah, so actually, so this may not be your the microscopic lattice. So this may be a coarse graining one. So on the very large square lattice, you choose a lattice point called 0, and some point far away, I call it 3, and this call it 1, this call it 2, and you can connect them. Yeah. Yeah. So actually, this requires you use a long string. Otherwise, if it's too small, it cannot actually distinguish two anyon. Because if you put the anyon too close, they mix. You cannot distinguish them.
Okay.
You need to measure 1 and 3. They are kind of far away. Okay. Now let me introduce another technical point. So here we try to use the polynomial to represent a Pauli operator on a square lattice. Let me do it step by step. So consider I have a square lattice and I have a Pauli on each edges. And Pauli here, if it's Pauli X, I use this 1, 0, 0, 0. And if it's Z, I use this 0, 0, 0, 0, 1, 0. So I use these two vectors to represent a Pauli X and Z here. And similarly, for this vertical one, I use these two vectors to represent the Pauli X and Z. And now, if I try to express the Pauli X and Z in other place, I apply some polynomial. For example, here is an X dagger. So it's moving this edge to the right to the 3 times. So this X dagger corresponds to the X cube times the vector of X1 for here. So you can see this operator has this X cube on this entry. The minus here means it's go from X to X dagger. And similarly, the Z operator here corresponds to this moving this Z to the right. So you need to apply the X squared on these edges. And these edges is Z1, 2 is exactly this column vector. So we need to apply this X squared on this one to obtain this one. So using this polynomial formula, we can efficiently express any Pauli operator into this polynomial column vector. So this can help us to compute a lot of things. Due to the time limit, let me just ignore some technical detail and go to the final result. Let me see. Yeah. So here we can repress the toric into some stabilizer, and the stabilizer into some polynomial. So this S1 means I have the Pauli X here and X dagger here. So this is X and X bar. X bar means moving to the left. And similar, this 1 minus Y corresponds to this Pauli X minus Y direction, like this. And similar for X2, it has a 1 minus Y, which means I have the Pauli Z here, and move to the Y here, it has a Z dagger to 1 minus Y. And similar, this one is a minus 1 plus X. Minus 1 here is a Z dagger, plus X is a Z here. So for every stabilizer, we can translate into some column vector of the polynomial. And we can compute how does the single Pauli operator excite these two stabilizers. So the detail from data is not very important, but let me show you how do we. So let me skip this one. So we can use this one to obtain the string operator for this example. So you can see the string operator is much more complicated. So in the original toric, the string operator is very simple, Pauli Z along one line. And here, this is something still string like, but it has a much more complicated structure. Yeah. But of course, we didn't optimize the string because we can always multiply some stabilizer to cancel out some Pauli Z. Yeah, but so far we just try to demonstrate our algorithm can apply to some model, and we can find all possible string operator, and we can compute the topological spin and also the braiding for this anyon. Okay, in this example, we find that this theory has 8 different anyon, and certain anyon has some non-trivial braiding. For example, the V1 and V8 they have non-trivial braiding -1. The V2 and V6 has a -1 braiding. So we can try to pair them up. Like a V1 pair with V8, V2 pair with V4, and V6 pair with V3, and V7 pair with V5. So this theory corresponds to 4 copies of a toric. So each pair corresponds to the E and N of the Z2 toric. So let me skip this one. So finally, I want to spend maybe 5 to 10 minutes to explain how do we study this example, the 3-3 BB code. So this is the example in the IBM paper. So how do we obtain this k equal to 16? And if we put it on a finite torus, how do we obtain k equal to 12? I want to have some theoretical understanding instead of some computational result. So first, the polynomial of that model corresponds to this one, the x plus x squared plus y cubed, and y plus y squared plus x cubed. So this S1 and S2 correspond as stabilizer for this BB code. And when we apply each Pauli, the Pauli will excite the S1 either on the F or G. So here we know the polynomial corresponds to F, and G will give you the trivial anyon. So the non-trivial anyon is become the polynomial ring quotient by the ideal generated by this F and G. So we want to know all possible polynomial, how many of them they are non-equivalent by these two polynomial F and G. Yeah. So there's a theorem. The number k equals the number of independent monomials quotient by this F and G. And the length L is basically your x, what kind of this L can be divided by F and G. So let me give you an example here. So given this F and G, first we compute its Grobner basis. The Grobner basis is basically just like a Gaussian elimination. So given a polynomial, we try to simplify the polynomial into some canonical form. So the theorem say, okay, these three polynomials, they generate the same ideal as this polynomial. And we can ask how many independent monomials are under these three polynomials. So you can see for the y direction, I can use one y, so y to the fifth, to generate all y monomials. And for the x1, after some trial, you can see this is independent, so x is independent, xy is also independent. But however, for the xy squared, you can use all this monomial times some translation of this HMN to generate this xy squared. So you can see for this f and g, it has a different independent monomial. So that's why we say there's a enn, and the total logical number is 16. So this is something you can compute by hand to verify. Okay, so this Hamiltonian equal to a copy of the toric. And the nice property of this approach is we can actually impose the later condition. So if I try to impose on the 12 times 6 torus, we can, with these two extra identification, so the x to the square equal to 1, the y to the 6 equal to 1, which means my lattice become periodic. And now I can just enter this f and g with all these two extra conditions. So this is just some mathematical comment. It's just some one-line computation. You can obtain the final Grobner basis of this polynomial. And compared to the previous one, is from 1 to the y to the degree 6. And now it only has a y to the degree 4. So which means the monomial generated is actually less than the original one. So here originally is from 1 to y to the 5th, and this is from 1 to y to the cube. So if we restrict this one by some finite torus, we can see the number of anyon decrease. It decreased from 8 to 6. So that's the reason why we only get a 12 logical qubit for this BB code on the finite torus. Okay, so due to the time constraint, I think I just skip the boundary part. So let me go to the conclusion page. And here, so in today's talk, first I described an algorithm to try to obtain all possible anyon information given the topological polystabilizer. And for the second point, I already skipped. In my second paper, I construct the correspondence between the bulk and boundary, and we show that all topological data can be obtained from the boundary computation. And actually, from the boundary is much faster because in the boundary we only need to deal with one dimension, and we can optimize our algorithm to conduct for a larger stabilizer code. And for the future work, I think we plan to generalize into some high dimension, although I mentioned in the 3D is much more complicated. And also we want to expand, explore the possibility for the beyond a billion anyon. Because so far the stabilizer code can only generate a billion anyon. And so we need to go beyond the Pauli stabilizer code. For example, we use some XP formalism, and possibly this can give us some non-billion fusion code. Okay, I think it's good to end here. Thank you for your attention.
We stop the recording.